Morning class. Today we will be studying concepts on deflection and the need for controlling deflection. So as an introduction, uh, I'd like to point out that deflection is a serviceability issue, and it has nothing to do with strength design. Okay, so let's have a recall on what serviceability means. So when you say serviceability, we are referring to most likely the function of the member of the structure or the structure itself. And just like flexure, deflection is actually manifested by what you call beam curvature. Okay, so we have studied that when a beam is loaded with some type of loading here, let's say we have a uniform load that is applied on top of it, the tendency of the beam is to bend. Okay, and this bending is in itself actually manifesting what you call deflection. Okay, so when the beam bends, deflection occurs. That's why flexure and deflection are uh, actually related, but by what you call the beam curvature. But the strength requirement is not an issue here because the strength requirement is taken care of by the resistance of the beam, which is actually computed on the basis of moment capacity. Okay, so this is the moment capacity of your member, while deflection is something we need to take care of and control because we want to preserve the use of the structure. Okay, so the function or the use of the structure. So in deflection control, as a summary, we have to deal with the working stress. Okay, so the WSD concepts will actually be a part of your deflection consideration and not the strength design concept. So the following are the main reasons why we have to control deflection. First, we need to control deflection because the structure imposed some requirements. Okay, so we need to follow some requirements, basing it on the code. Okay, and not just the structural code, but all codes that might be uh, contributory to safety. Okay, including the National Building Code in general. And this requirement must be satisfied in order for us to make sure that we comply with the standards of deflection control. So example of that is the requirement on drainage, okay, on the roof of a structure. Okay, so we need to bear in mind that drainage has something to do with the slope uh, maintenance of your beams and slab members. If the slope of the beams and the slabs are not within the limit, then you will be having problems with the function or use of the structure as to drain water from the roof. For other requirements such as uh, the functionality or the use of the structure itself, maybe for entertainment and sports, the bowling alleys, the billiard halls must actually be leveled so as not to disrupt, okay, the function and use of such structure. For printing press or newsletter production buildings, so we need to see to it that when the equipment vibrates, the deflection and the vibration shall be controlled to make sure that the printouts and the newsletters are within the requirement uh, set forth by the printing industry. Okay. So for number two, we need to ensure that the non-structural attachments to structural members will not be affected by uncontrolled movement. And what does this mean? Um, the buildings are made up of the major elements or the main structural elements, and also the minor or the non-structural attachments or elements. And if these attachments will simply be controlled by the movement of the members such as beams, slabs, walls, etc., then the attachments like ceiling, partitions, doors, windows, and other finishes might be affected. Like the doors might not close, the ceiling might be what is falling off. Okay, the glass partitions might break when deflection are excessive. The finishes might fall off or might be damaged, etc. So we need to see to it that these are properly taken care of in the deflection control. And the last, but not least, of course, on the main reasons is the psychological impact or psychological effect on the occupants. Okay, so this has something to do with the occurrences of excessive deflections and vibrations. Okay, by the way, class, deflection and vibration are just the same in context, because deflection is simply a static phenomenon while vibration is a dynamic phenomenon. So when we talk of deflection, we can actually relate it to vibration. Okay, so a deflection that is moving or is not steady is actually the vibration of such member. It can be measured in terms of one over the other. Okay, so as stated earlier, deflection is an elastic problem. It's not a strength design problem. So a beam which is designed in the working stress design method is more likely to pass the requirement for deflection rather than the strength design method. Why? Because the WSD method will give you okay, larger sections than the strength design method. That's why This method is safer in terms of deflection. Okay, so this is better in terms of deflection. Okay, but of course, when you say better, it does not necessarily mean that you have to use it, no? So, if you use a better method in terms of deflection, but it's very expensive, so you might as well think twice. Okay, so for this, the justification is because of this practically larger and stiffer beam sections, which makes it very good in terms of deflection control. So a balanced design with working stress normally have stresses below the ultimate strength of both steel and concrete, and in terms of raw, this is below half the balanced steel ratio raw B. Okay, so when your raw is small, then your section is big, and that is a more expensive design because you'll be needing larger formworks and heavier construction scaffolds to withstand the process of erecting your structure. So in the strength design approach, beams that use uh, high strength concrete and steel results in smaller sections. So that's why deflection control is very necessary, and it is an issue when your methodology in design is the strength design method. Okay, let's proceed now with some code guidelines. Start with we will be guided accordingly by the codes in order to limit and control deflection. And one old way of doing it is by simply looking at the H over L ratio, okay, which is more or less 1 over 20. In the old codes, you just check your H, okay, is equal to L times 1 over 20, okay. So if you know the length, you just divide it by 20, you get the height of your beam, okay, or slab. So this refers to the height of your beam or your slab. But of course, this is an old rule of thumb that was used in the earlier days. You can look into the reference of Wang and Salmon, section 14.1, regarding this. So a better way of dealing with deflection control is by using the ACI code, no? So the limitation of such is actually referred into the section 9.5.2, wherein the use of the section is only limited for non-pre-stress members. When you say non-pre-stress, we are referring to what? These are the RC members, okay? So these are the reinforced concrete members. And this must be members that does not support attachment likely to be damaged by large deflection. This phrase here is often used in the code, and it simply means that whenever your member does not support any attachment at all that are very critical in deflection situations, then you don't actually have to worry about deflection. Okay, so RC members which are not supporting uh, any element attached to it, and it might be damaged by large deflection. It simply means that when deflection happens to the member, there's no danger of any violation on the first three reasons here. Okay, you don't have to worry about the requirement, you don't have to worry about the attached elements because there are no attached elements, and you don't have to worry about any psychological distress that might happen to the occupants. Okay, because uh, your code is actually sufficient to guarantee any danger uh, when you limit your deflection control on the basis of the use of the ACI 9.5.2. Okay, and what is ACI 9.5.2? ACI 9.5.2 gives you the freedom to use the table here. Okay, so this is actually a reference on ACI 9.5.2 that we can use table 9.5a to check for the minimum thickness of the non-pre-stressed beam or one-way slab if you don't want to calculate deflection. Okay, so here is the 1/20 that I'm referring to on the old codes, and then it extended up into some improvement on the choice of what particular support condition you might have. Okay, you might have a simply supported beam, you might have a one end continuous, you might have a both end continuous, and a cantilever beam here. Okay, so for solid one-way slabs, this is now the row to choose the K requirement. Okay, and this is for beams or ribbed one-way slab. Okay, normally we do use this for beams. Okay, and we use this for one-way slabs. Okay, so how do we use this? It's as simple as let's say if your L is given to be 6 meters, you simply divide 6 all over 20, and so this is more, I think, point 30. Okay, is this yes, point 30. If this is in meter, this is in meter, which means to say that your limit for such one-way slab must be 0.30 meters. Okay, so considering simply supported condition. Okay, so we have this simply supported beam. Okay, for a simply supported sorry, this is a simply supported slab. Okay, not beam. Okay, for a simply supported beam, it will be L over 16. Okay, so L, if L is 6.0 meters, so you simply divide 6 all over 16. So this is, I think, greater than 0.30. So we can make use of a calculator and try to check for the minimum. So this is 6 divided by 16. So we get 0.375 meters. And this is for your simply supported beam. Okay, so something like this. No? If it's a one-end continuous, you use this for slabs, you use this for beams, etc. So it's a simple requirement that you can use, but again, this is only limited to the condition that your member is not attached to elements likely to be damaged by large deflection. Okay, so you don't have to calculate, you just use the table when you want it. So for lightweight concrete, there's some adjustment on the use. A multiplier was made here, but actually we are not using lightweight concrete more often here in the Philippines. No? So you just maybe try to use this whenever we encounter some problems in doing so. And for Fy other than 60,000 psi, the value shall be multiplied by 0.4 plus Fy multiplied by 100,000. Okay, so there's a limitation here, class, that your Fy must be always a grade 60 reinforcement. So if I give you a problem where Fy is, say, 40, grade 40 or 40,000, I have to use this as my multiplier to this uh, value here that was obtained from this ratio. Okay, so I just insert 40,000 divided by 100,000 there, so I get 0.4. So this is 0.8 of 0.375 or 0.8 of 0.3. Okay, if my Fy is not 60, or it has a yield strength other than 60,000 psi. So limiting computed deflection on the basis of another guideline. So you will be using this if you are forced to compute. Okay, calculate the actual deflection. So these are the limiting, and these limiting are a little bit confusing at first. So I'll explain to you this further later. But when do you use this table 9.5b? Whenever your member has some elements or attachment that are likely to be damaged by large deflection. Okay, when these member are likely to be damaged and they are attached to this, so there is an attachment to this type of deflection which are likely to happen, then we use this table here. Okay, so deflections must be computed when the actual thickness of the member, which are not supporting attachment a while ago, is less than that specified in table 9.5a. Okay, so example, if I have my thickness or height less than this, and I want to use that thickness, the actual thickness, and my my member is actually attached to elements that are likely to be damaged by large deflection, then I have to use table 9.5b in order to check whether my calculated deflection is safe in regards to this limitation. So I will no longer consider the limitation set forth on 9.5a. Okay? Okay, so we will be looking into that later. Okay, I'll explain to you some scenarios. So these are now the scenarios on the type of members. So what are the types of member? We have actually, in general, two types only. Okay, so these two types are for floors and the roof. Okay, sorry, these are for non-structural attachment. Okay, and these are attachments. Okay, so these first two here are actually not supporting. Okay, so they are not attached, while these two here are actually supporting or attached. Okay, when you are talking about attachment, you are talking about supporting. Okay, so they are just the same word. So example is when the beam is supporting the slab, or when the slab is supporting the water tank. Okay, when the beam is supporting the door, the windows, the partitions, so you call that attachments or supporting. When they are not supporting, they are not attached. Okay, so not supporting or attached, this is supporting or attached. Okay, okay, when we're referring to non-structural, those are the minor elements in your a building, like the windows, doors, etc. Okay, the ceilings, the cabinets, those which are attached to it, the finishes, the tiles, okay, the acoustic boards. Okay, so those are the non-structural attachment or elements. So we have actually 4 types of member, but we can summarize this into these two. Okay, these two here are for flat roof and for floors not supporting, and these two here are for roof and floors which are supporting. Okay. Okay, so this is a continuation of this. This is also a number, the 1, 2, 3, 4. Okay, 2, and these are the 3 and the 4 are mixed. Okay, they are mixed there. So what are you going to do? So when you are using the type of member 1 and 2, you ought to solve only immediate deflection. I will discuss to you what are immediate deflection. So this is due to live load. So its a symbol is delta I LL. Okay. So immediate delta is deflection due to live load. Okay. So for the 3 and 4, there are two deflection consideration here. Okay. that part of the total deflection occurring after attachment of the non-structural elements, which is, okay, the sum of the long-term deflection due to all sustained loads and the immediate deflection due to any additional live load. So simply, this is simply delta I LL plus what is deflection due to sustained loads. We can call it delta sustained. Okay, so this sustained load I will be discussing again when we go to the computation. And take a look at the value of the limiting deflection. Okay, so this must not exceed this, or else if it exceeds the value, your serviceability fails. Okay, so the limitation will tell you if your member deflection is controlled or not. Okay, so this is controlled or not. So this will tell you later. And take a look. This is the biggest. The biggest deflection is this one. This is number 1 in terms of the biggest value, and this is the last. Okay, the smallest. This is the third, and this is the second. So which means that the most critical is type member 3, type member 4, then it follows 3, and then type member 2 rather, type member 4, and type member 1. Okay, this tells us which is the most critical. The most critical is 3. This is member number 3. The second is member number 2. Then the third is member number 4. And the last, most critical, is member number 1. Okay? So if you look into the hierarchy of which is more serious in terms of deflection requirement, you look to this. Okay, this is the most serious, number 3, and then this is number 2, and then this is number 4, and then number 1. Okay, so let's stop at this point to entertain some of your questions. We continue on the concepts on how to calculate deflections on the next video presentation. Okay, so I'll see you on the next video.